let's get started. Thanks for coming despite the rain. But you know, at least we can feel lucky that the sun rose today, because we have a lot more to do, and it'd be hard to do if the sun stopped rising. So okay, so we were talking about MGFs last time. We've done all the theory that we need for MGFs, but I'm not sure that the intuition is clear enough yet, and there are some important examples. So I just want to start with a few examples of MGFs. We already have all the theorems. Okay. Especially, you know, how do we work with MGFs for some of the most important distributions, such as exponential, normal, and Poisson, just to show you how the MGFs are useful for some of those famous distributions. Okay, so let's start with the exponential. And we talked before about, so this is the expo MGF. We talked before about the fact that if we have exponential lambda, we can always find a constant to multiply by to make it exponential 1. So let's just start with the exponential 1 case, because that's simpler. That is lambda equals 1. Let x be exponential 1. And suppose that we want to find the MGF and find the moments. Okay? Find moments. And this will really show you why it's called the moment generating function. That doesn't actually, I didn't talk about where did the word moment come from. It comes from physics, so those of you who've done like moment of inertia and stuff, there's like there's actually a pretty strong analogy between variance and moment of inertia. That doesn't answer the question for where did the word moment come from in physics, but you can ask the physicist that. But it came into statistics via physics because of this analogy with moment of inertia. Anyway, so we have an exponential, okay, and so let's find the MGF. Well, by Lotus, that's a pretty easy calculation. M of t. Remember, just by definition, it's just the expected value of e to the tx. And this is, this is a perfectly valid thing to write down. This e to the tx, that's just some random variable. We're taking its expectation, and then we're viewing this as a function of t. And I pointed out last time t is a dummy variable, so I could have just as well said m of s equals expected e to the t, e to the sx, or whatever you want to call it that doesn't clash. The interpretation is just that this is a very, very useful bookkeeping device for keeping track of moments, and it's another way to describe a distribution rather than a CDF or a PDF. Okay, so let's just compute this thing. Well, this is an easy Lotus problem, because by Lotus we can just immediately say this is the integral 0 to infinity, e to the tx, e to the minus x dx. Right, that's just immediate from Lotus. Combine the two exponentials, so that's e to the minus x times 1 minus t dx. So that's just an easy integral, right? So that integral, well, actually, one way to do it is just to do the integral. Another way to do this integral is to recognize this as another exponential PDF with a different parameter and put in the normalizing constant. And you'll get 1 over 1 minus t, and this is for t less than 1. If t is bigger than 1, we have some problems here, because like if you let t be 2, for example, then that would be 1 minus 2 is negative 1. You get e to the positive x, which would blow up. But as long as t is less than 1, this will be okay. It'll be exponential decay, not exponential growth. So we have to assume t less than 1. But that's okay, because we talked last time about the fact that we wanted to have some interval, like I called it minus a to a, on which this is finite. So in this case, it's finite everywhere to the left of 1, right? So in particular, you could take some interval, like say minus 1 to 1, open interval, on which it's finite. So this is a perfectly valid MGF. Okay. So now we want to get the moments, right? So from what I said last time, we could take this thing 1 over 1 minus t and start taking derivatives. So, and plug in 0. So it would be true that m prime of 0 would be the mean, and m double prime of 0 would be the second moment. And once we have this and this, we could easily get the variance. We already talked about the mean and the variance of the exponential. So you could do this and check that it agrees with what we did earlier through Lotus. Okay, and then the third moment would be the third derivative evaluated at 0, and so on, right? So we could do that, but that's kind of annoying in the sense that you have to keep taking derivatives. Now, for this function, taking a bunch of derivatives is not too bad, okay? But still, a much better way to do this is to recognize the pattern, right? A lot of this is about pattern recognition, okay? Where have we seen 1 over 1 minus t before? Geometric series, right? We keep using the Taylor series for e to the x and geometric series over and over again. It can go in both directions, right? You can have the geometric series result and write it as a geometric series, or you can have a geometric series and simplify it to this. Anytime you see 1 over 1 minus something, you should be thinking that may have something to do with the geometric series. That may be a useful interpretation, it may not, but at least that the idea should pop into your mind just because you see this pattern, okay? So if we do that, we get 1 over 1 minus t equals just a geometric series. The sum t to the n equals 0 to infinity. And this is valid for t greater than, for absolute value of t less than 1. That's when this converges. By writing it this way, we don't actually have to do derivatives. We're just looking at this series, okay? And then we're just going to read off the moments. So the only thing we have to be careful about is the n factorial. Because I said with the MGF, you take the Taylor expansion, and the moment is whatever is in front of t to the n over n factorial. I don't see an n factorial here. But that's no problem, right? You just multiply and divide by n factorial, because we need the n factorial there. So I'll just multiply by n factorial, t to the n over n. Now, n factorial, now this matches exactly the pattern that we talked about last time about, you know, whatever's in front of the t to the n over n factorial, that's the nth moment. So that's the nth moment. So we immediately know now that e of x to the n equals n factorial for all n. So instead of taking derivatives over and over again, we simultaneously get all the moments of x, okay? So that's nice, right? Didn't need to take any derivatives. So that, by the way, that's kind of like the coolest thing about MGFs is the fact that if you, just in general, not necessarily for this example, if you want to find the moments of some distribution, by Lotus, you would think you have to integrate, right? You want e of x to the n, so you're going to integrate x to the n times a PDF. That may be an incredibly difficult integral. But the MGFs, once you have the MGF, we're taking derivatives, not integrals. So it's pretty surprising, to me at least, that you can do derivatives of the MGF rather than integrals of powers of x. Derivatives are much easier usually than integrals, so that can save a lot of work. So let's just quickly see what happens if it's exponential lambda, where lambda is not necessarily 1. So now let's let y be exponential lambda. And then let's just convert it, just to see how to apply this. Convert it, well, exponential. So we talked before about the fact that if you multiply or divide by lambda, now it may be hard to remember, should you multiply by lambda or divide by lambda, but there's an easy way to see that. Let's just let x equal lambda y. So I knew to multiply by lambda rather than dividing because we know that exponential lambda has mean 1 over lambda. So if you multiply by lambda, now this has mean 1. And we showed that this is, in fact, exponential of 1. So we've converted it to this case. In other words, y equals x over lambda, and we can take nth powers. So now we immediately have the moment of the nth moment of y. Expected value of y to the n equals expected value of x to the n, which is n factorial, divided by lambda to the n. Okay? So I didn't do any calculus here. I only used the geometric series. And it's just, you know, we could have directly done something similar to this for y, but I think it's easier working with the exponential 1 and then converting it back. Similarly, at the end of last time, we derived the MGF of the standard normal, okay? Now, if you want any normal, mu sigma squared, then you just write it mu plus sigma z, right? And then you know, you can get its MGF very easily. So a lot of times it's easier to work with the standard normal. Okay, so speaking of standard normal, let's actually get the normal moments now. We already know the odd moments. So the problem is, you know, let z be standard normal and find all its moments. Okay? We already know that the first moment is 0 and the second moment is 1 because it means 0 variance 1. We already know that the odd moments are all 0. That's just by symmetry. We mentioned that fact before, but you know, you should check for yourself that that makes sense. That, you know, to practice the symmetry. Because if you write down the integral using Lotus, you would be integrating an odd function symmetrically about 0, so the negative area cancels the positive area. So you don't need to do any work to get this, just use symmetry. Even moments, though, that seems pretty hard. I mean, we already know e of z squared, and we did that, you know, by doing some integration stuff. Now if you want e of z to the fourth, you know, if you use Lotus, you're going to have to integrate z to the fourth times the normal PDF. How do you do that integral? I don't know. I mean, you can try doing some substitutions. You can try doing integration by parts. And, you know, you could easily spend a couple hours doing that integral. And it's possible to do it, but it's not easy. It'll be a lot of work. And that would just be the fourth moment. And then you say, well, what about the sixth moment? What about the eighth moment? Right? So that's not a very, very efficient way to do things. Just doing a lot of nasty-looking integrals. Okay, so let's use the MGF instead. The MGF that we derived last time is the function m of t equals e to the t squared over 2. So that at least gives us an approach to getting the moments that doesn't involve having to figure out how to do these integrals, okay? It's something more straightforward. You know, like for derivatives, we have the chain rule, the product rule, and so on. There's no chance that you can't do this derivative if you know your chain rule and product rule and stuff like that. Whereas for integration, you may just not know how to do the integral. Okay, so we could take the derivative of this, use the chain rule, and we're going to get a t that comes out in front because of the chain rule, and then we take the second derivative because then there's going to be a t out there after the first derivative. Then we'd have to use the product rule. Okay, and then we take another derivative. And then, you know, you have two terms, and then the terms start, you know, multiplying, and you get more and more terms to deal with, and it would get more and more tedious and ugly the more derivatives we took. It's still something that, you know, you can do, just it's pretty mechanical, but it's tedious, and we want to avoid tedious stuff. Okay, so here's a much better way to think about it. Over there with the exponential, I emphasize just the pattern recognition geometric series. Let's apply the same thinking again. Pattern recognition, this is e to a power, okay? The Taylor series, unlike the geometric series, the Taylor series for e to the x converges everywhere. So I can immediately just write down the Taylor series for this without taking any derivatives. This is just the sum of t squared over 2 to the n over n factorial. Right? Because the Taylor series for e to the x is valid everywhere, so in particular I can plug in t squared over 2. Okay, so this is a much, much better way to do it than to start taking derivatives of this. So let's simplify this. This is the sum. Notice that we're only going to get even powers of t, which makes sense because this is an even function. So it's going to be t to the 2n, and there's a 1 over 2 to the n in the denominator, and there's an n factorial. Okay? So that's what it is. Now, same as over there, we just have to read off the moments. The only thing you have to be careful about is the fact that there's a 2n here in the exponent, and there's an n factorial there. So there's kind of a mismatch right now, okay? To get the 2nth moment, we want the 2nth moment, because 2n is just an arbitrary, you know, even number, okay? So we want the 2nth moment. So the 2nth moment, we want the coefficient of t to the 2n over 2n factorial. We don't have a 2n factorial. Well, that's okay, just put in 2n factorial. As long as we multiply by that, it's okay. So I just multiplied and divided by 2n factorial. It immediately tells us the answer. The expected value of z to the 2n, so that's just an arbitrary even moment. We already have the odd moments, is just the coefficient of t to the 2n over 2n factorial. That's everything that's left. That's 2n factorial over 2 to the n factorial. And let's just check whether this makes sense in the cases we know. If n equals 1, n equals 1, this is 2 factorial over 2 times 2. Wait, n equals 1, so 2 times 1. Okay, so that's 2 divided by 2 times 1 is 1. So e of z squared equals 1. And that's what we expected because the variance is 1. And let's just do a couple more. N equals 2. So then we get the fourth moment, z to the fourth. N equals 2. 4 factorial is 24 divided by 8. 24 divided by 8 is 3. So the fourth moment is 3. And the next one, e of z to the sixth, is going to be 3 times 5 equals 15. And you'll see, I'll write it as 1 times 3 times 5. You'll see the pattern is if it's 1 times 3, 1 times 3 times 5, 1 times 3 times 5 times 7, and so on. And this is not the first time that we've seen these numbers, or at least if you've done the strategic practice problems going way back. That was the number of ways to break 2n people into n partnerships. And there was a story problem there. We could either write it this way or as a product of odd numbers. So kind of a surprising fact, or at least I found it really surprising that this same expression comes up for even moments of the normal as it's the same number as breaking up people into partnerships and counting number of ways to do that. And I thought that was kind of mysterious. It turns out that it's not a coincidence, but there's kind of a very deep combinatorial explanation for that, which I can't get into. But there is a reason for that. Anyway, that gives us all the moments of the normal distribution now, without doing any calculus. So that's nice. Okay, so one more MGF problem. We haven't talked yet in class at the MGF of the Poisson distribution, so let's do that. So, Poisson, we know that the mean is Poisson lambda. We know it has mean lambda and variance lambda, but we haven't computed any other moments. But mainly for the Poisson, I wanted to show you the other, like I said last time, there are 3 reasons why the MGF is important. And those examples illustrate the fact that, why it's the moment generating, because we generated all the moments. Okay? Well, but for the Poisson, I want to show you the other important reasons. So let's let x be Poisson lambda and find its MGF again. Well, let's just use Lotus. The expected value of e to the tx equals the sum. So Poisson takes non-negative integer values. So I'll just say k equals 0 to infinity. E to the tk, right? It's just Lotus. And then times the Poisson PMF, e to the minus lambda, lambda to the k over k factorial. Okay, looks like a kind of ugly sum. Well, actually, you'll find that this sum is an example on the math review handout, so I was planning far in advance. But you don't have to memorize that or anything. This is just another example of pattern recognition dealing with a series. It looks a little ugly when you first see it, but this is actually easy once you're familiar with the pattern, right? So e to the minus lambda comes out because that's just a constant. Look at what's left inside. We have this is e to the t to the k, and this is lambda to the k. So together that's lambda e to the t to the k, right? So all that's left is the sum of something to the k over k factorial. That's just the Taylor series for e to the x again. So this is very easy, you know, once you've mastered the Taylor series for e to the x. So we can just immediately write that down then. It's the Taylor series for e to the x evaluated at x equals lambda e to the t. Okay? So we can simplify that a little bit. It's e to the lambda e to the t minus 1. So that's the Poisson MGF. And it's valid for all values of t because the series converges for all t. Okay, so that's the Poisson MGF. So one thing we could do with it is to start taking derivatives or trying to expand it or whatever to get the moments. But I'm not doing this example because I want to do moments. So I want to show you the other applications of MGF. So now let's let y be Poisson of mu. So we have two Poissons now, not one Poisson. And suppose that x and y are independent. And the problem is find the distribution of x plus y. So we want to study the sum of two independent Poissons. Okay, so that's called a convolution. We'll come back to convolutions later on in the semester, but you know, in general it can be nasty. But I pointed out last time that for MGFs, you can just multiply the MGFs. That's easy. Whereas doing a sum or integral could be pretty nasty. Okay, so all we have to do is multiply the MGFs. That is, I'm just going to take the MGF of x times the MGF of y. So here's the MGF of x, e to the lambda, e to the t minus 1. MGF of y is going to be the same thing, except that the parameter is now called mu instead of lambda. So that's going to be e to the mu, e to the t minus 1 equals, and let's just simplify it, that's e to the lambda plus mu, factor that out, e to the t minus 1. That immediately tells us that x plus y is Poisson lambda plus mu. Because of the fact, we didn't prove this theorem. As I said, that's a really difficult theorem, but that is a theorem that this is the Poisson lambda plus mu MGF. There's no other distribution that has the same MGF. So this is therefore the only possibility. By the way, it was obvious that the mean had to be lambda plus mu by linearity. So this we already knew. The interesting part is that it's Poisson. The sum of independent Poissons is still Poisson. Most distributions don't have such a nice property. Like you add independent versions of them, and usually you get some other family. Here it's still within the Poisson family of distributions. Okay, so that's a very, very nice property of the Poisson. And a common mistake with this is to ignore the assumption that x and y are independent. So to justify being able to just multiply the MGFs, we need x and y to be independent. So just to see a quick counterexample, if they're not independent, if x and y are dependent, well, the most extreme case of dependence that I can think of is when x equals y. Okay, so let's just see why this doesn't work when x equals y. Well, obviously, if x equals y, then x plus y is 2x. And that's not Poisson. Why is that not Poisson? Yep. Okay, so that's a good way to think of it with the MGF. If you take the MGF of this thing, you're going to get a 2 in there, and what are you actually going to have? You're going to take the expected value of e to the 2tx, so you would replace t by 2t, so you would get a 2t up there, and that doesn't look like a Poisson. Now, so that's close to a proof, but it's a little more complicated than I was thinking of, and you would still need to say, like, could there be some miracle of algebra that would reduce that back down to, it's not true, right? If you put a 2 there, it's not of this form. But still, you know, what if you just didn't think of the brilliant algebraic way to simplify it down? Yeah? Yeah, that's the simplest way to see it. Wow, so what she just said was that this thing is even. That's one good way to see it. A Poisson has to take on any possible non-negative integer value. This thing is always an even number, so it couldn't possibly be Poisson. That's the simplest way to think about it, just looking at what are the possible values. Another way to see it would be to compute the variance, the mean and variance. So the expected value of x plus y, which is 2x, would be 2 lambda. So if it were Poisson, it would have to be Poisson 2 lambda, because that's the mean. But the variance of 2x is 4 lambda, because the 2 comes out squared. For a Poisson, the mean always equals the variance. For this thing, the variance is double. Intuitively, that should make sense, because you're adding the same thing to itself. That increases the variance compared to, if you add independent things, then you might expect, you know, if one thing happens to be very large, the other thing might offset it, right? But if you're adding the same thing to itself and it happens to be large, then you're adding the same large thing twice, okay? But I've seen that a similar mistakes, so this is kind of like an easy counterexample, but I've seen similar mistakes in Stat 110 many times where maybe we have something like a sum of x1 plus x2 plus x3, and a student then just replaces them all by and their IID, and then a student replaces them all by x plus x plus x and get 3x. But you know, x is not independent of itself, and that's the same mistake as this. So I wanted to mention that counterexample. Okay, so, and there's other ways to see it too. But we just talked about 3 reasons why this was not Poisson. 1 using the MGF, 1 by looking at the possible values, 1 by looking at the mean and variance. So hopefully you're convinced now that that's not Poisson. Okay, so next major topic in this course is joint distributions. That is, you know, something we've dealt with a little bit before, but just like bringing it in as its own topic in its own right. So joint distributions just means, you know, how do we work with a distribution of more than one random variable, okay? So that's why everything in this course is cumulative, right? Because if you don't fully understand the CDF of one random variable, then it's going to be really hard to understand the joint CDF of more than one random variable, okay? So joint distributions, you know, we've already talked about independence versus dependence, right? If you have independent random variables, then joint distribution just means multiply the individual CDFs or the individual PDFs, and it's pretty straightforward. You know, remember the slogan, independence means multiply, okay? But in general, you know, we need to have some tools and notation and so on for dealing with dependent random variables. Maybe just 2 of them, or maybe, you know, maybe 1 million of them, okay? So we're going to talk about joint distributions. And I think the best way to start is in the simplest case, where we have 2 random variables, and let's even just say they're 2 binary random variables. So we can think of this in terms of 2 by 2 tables. And this may seem really simple. And I hope it seems pretty simple, because then if you understand this simple case really well, it'll give you a lot of intuition for the more complicated case. Okay, so we'll start with the simple one, where x and y are Bernoullis, possibly dependent, possibly independent, and possibly the same p, possibly different p's. I'm not saying they're both Bernoulli p with the same p. Okay, then we can think of this in terms of 2 by 2 tables. So we could draw an example like this with a table, and we could just tabulate values, where here's x equals 0, x equals 1, and y equals 0, y equals 1. Okay? And then to specify a joint distribution, all we have to do is put in 4 numbers here that are non-negative and add up to 1, right? Any 4 numbers you want, as long as they're non-negative and add up to 1, that will be a valid joint distribution. So remember, for, you know, PMFs, to be valid, a PMF, just non-negative, adds up to 1. Completely analogous. It just now it's in 2 dimensions instead of 1 dimension. Okay? So we could just make up 4 numbers that add up to 1. And I guess we're going to talk about some of the general definitions here. So this is for the specific case, but let's also talk about the general case. So if we have x and y, first of all, they're joint CDF. It's completely analogous to the individual CDF. So the joint CDF is it's a function of 2 variables now. F of xy equals the probability x less than or equal to x, y less than or equal to y. Similarly, we have a joint PMF in the discrete case. Which would just be the probability that x equals little x, y equals little y, right? So if we just had this part, that's the PMF. The joint PMF means we're considering both of them together, okay? Now, in the case where they're independent, if x and y are independent, that means that this joint PMF is the product p of x equals x times p of y equals y. So that's called the joint CDF, joint PMF. And now, this is when we're considering them together, right? Because it's comma within the same p, right? It's considering them jointly, okay? If they're independent, that's equivalent to independence, is that you can split this up, okay? So now there's another concept that we need called marginal. The marginal distribution, marginal just means take them separately. So the marginal distribution would, for x, would be probably x less than or equal to x, is called the marginal of marginal distribution of x. Similarly, marginal PMF would just be just this part, okay? So therefore, in words, we could say that marginal independence means that the joint distribution, the joint CDF is the product of the marginal CDFs. Okay, and similarly, we have, we can continue this over here, we have the notion of a joint PDF. I'm doing kind of discrete and continuous together because they're analogous to each other and they're analogous to the one-dimensional case. So joint PDF, which we might write as little f of xy, such that, so this would be the continuous case in 2 dimensions. What does it mean to be a joint PDF? Just like in the one-dimensional case, the PDF is what you integrate to get a probability, okay? 2-dimensional case, same thing. If we want to know what's the probability that x and y are in some set, let's say xy is in some set B, where B is some region in the plane. Maybe it's a rectangle, maybe it's a circle or something. It's just some imagine some area in the plane. Then what we do is integrate over that region f of x, y dx dy. So that's the first time we've written down a double integral here. But as far as we're concerned, for the most part, double integrals, for this course, the double integrals, we're not going to need to do a lot of them. And when we do, normally we can just think of it as one single integral and then another single integral. So just do 2 integrals. But the intuition should be clear, right? That the PDF is what you integrate to get a probability. So it's completely analogous. And so independence means that we've already talked about this before. I'm just using new terminology for it. Independence means that the joint x and y are independent if and only if the joint CDF is the product of the marginal CDFs. So I'll call that, just for emphasis, I'll call it would be confusing to use the same letter F here without any clarification. This is the marginal CDF of x. This is the marginal CDF of y. This is the joint CDF, okay? So it says that instead of having to do some kind of complicated joint thing, I can just find the probability of this event times the probability of this event. So that's the definition of independence. But we've seen over and over again that usually it's easier to use PDFs or PMFs. So it's equivalent. It's not too difficult. It's a little bit tedious, but with some algebra, we can show that it's the same thing as saying the joint PMF is the product of the marginal PMFs. That's in the discrete case. And in the continuous case, that the joint PDF is the product of the marginal PDFs. And I want to emphasize that this has to be for all x and y, not just for x and y that make this thing positive. You have to pay attention to the zeros also. We'll see an example like that later. So for all real x and y, we can't restrict it. All right, so coming back to this simple little example, we can make up any four numbers we want as long as they're non-negative and add up to 1. So I made up four numbers just for the sake of example. 2/6, 1/6, 2/6, 1/6. So I made up a simple little example here. And I could ask the question, are x and y independent? And to answer that, we need to say, well, two ways we can think about it. One would be, so I wrote this in terms of joint CDFs, joint PMF. We could also write something like conditional, right? That is, independence means if you want the distribution of y given that x equals something, it doesn't actually depend on the x part. So it's the same as the unconditional distribution. Okay? So anyway, so each number in this table is one of the joint probabilities, right? So 2/6 is the probability that x and y are both 0. 1/6 is the probability that they're both 1, and so on. Okay? So to check that they're independent from the definition, well, what that means is we first need to find the marginal distributions and then check that this is true. Okay? Now to get from the marginal to the joint, so here's just quickly how do we get marginal distributions? Getting marginals is actually pretty easy from the joint distribution, because, well, let's just do the discrete case first. If we want to know the marginal distribution of x, that is the marginal PMF, then just by the axioms of probability, all we have to do is add up the different possibilities for y. So that's the sum over all y, p of x equals x, y equals y. Okay? Because just the axiom of probability, right, that we're adding up disjoint cases. The union is this. You can also write it as a conditional. You can also think of this as the law of total probability and write given y equals y times p of y equals y. It would be the same thing. Okay, that just says add up, x equals x, but y could be anything, so we sum over y. So that's called marginalizing over y, that we're just summing up. We start with this thing that's a function of x and y, sum over all y, then we just get a function of x. And in the continuous case, let's get the marginal, so that's the discrete case. In the continuous case, let's say we want the marginal distribution of y. Similarly, you can get the marginal distribution of y. I'm not going to write the same thing again. If you want the marginal PDF, so this is the marginal PDF of y. Marginal just means viewing it on its own, as its own thing, right? Then all we have to do is integrate, completely analogous to this, integrate the joint density, f of xy, xy, integrate over all x. That's just the continuous analog of that. Here we're summing over all values. I swapped the x and y here just for variety. Here we're summing over all values of y. Here we're integrating over all values of x. The joint density, okay? So we can go in that direction. This is getting marginal distributions from joint distributions. You can't go in the other direction, because if we only know the marginal distributions, that doesn't tell us anything about how x and y are related to each other, right? So you can't go in the other way. But you can go from the joint distributions to the marginal distributions. Okay, so for this example, let's get the marginal distributions. So what's the probability that y equals 0? Well, obviously we're just adding this case plus this case, right? Because those are the two cases where y equals 0. So we add those two cases, we get 4/6. Add these two cases, we get 2/6. And for the other way around, if we want the probability x equals 0, just add this case and this case, and we get 3/6, or 1/2. This one plus this one, 3/6. And by the way, one thing you have to be careful about is the terminology in economics and statistics is very different. And when you take an econ class, you always hear about marginal revenue and marginal cost and things like that. And usually, like in AP econ, then they don't want to use calculus, and so they explain everything as incremental. If you do one more unit of something, then what happens? And then later, when you actually see what's going on with calculus, you realize that in econ, marginal means derivative, and in statistics, marginal means integrate. So it's completely opposite meaning. And I don't know where the econ term came from, but you can see here where the statistics term came from, because it's called marginal because we write these numbers in the margins. So that's a marginal distribution. So once you understand this 2x2 table, you basically have the key intuition into joint distributions. So, okay, so in this case, here they are independent. In this example, to check that they're independent, there are other ways to do it, but just to check it by the definition, what independence means is that to compute any of these entries, let's say 2/6, all I need to do is find the probability that x equals 0 times the probability that y equals 0. So I would multiply 3/6 times 4/6, which is 1/2 times 2/3 is 1/3, which is this. So to get this number, I could multiply this times this, and so on. So you could check these four numbers. So each of these joint probabilities is obtained by just multiplying two marginal probabilities. So that means they are independent. Whereas, you can make up your own examples. If you just, here's kind of an extreme example. It doesn't need to be this extreme. But I can pick whatever numbers I want as long as they're non-negative and add up to 1. So for example, I just made one up here where these non-negative add up to 1. So this is a perfectly valid joint distribution. But you can see right away that with this 0 means it's not going to be true, that if you multiply, you can't obtain it that way, because if you add, do the marginal thing again, 1/2, 1/2, and this is 1/4, 3/4, and you multiply 1/4 times 1/2, you don't get 0. So this one would be dependent. This one is dependent. You can make up your own examples. It doesn't have to have a 0 in it to make it dependent. That was just an easy extreme case to see what's going on. Okay, so this is a simple two-dimensional discrete example to think about. Let's also do one simple continuous example, just to have some more intuition on what this all means. So the simplest way to start, I think, would be with a uniform distribution. What does uniform in 2 dimensions mean? So let's consider, as an example, what if we have uniform on the square that's all xy such that x and y are both between 0 and 1. So we just have this square here. We can draw our coordinates and have a square here where this is 1 and this is 1. Okay, so we have this square, and we want a distribution that's uniform over this square. So remember, in the discrete case, in the one-dimensional case, uniform meant that the PDF was constant on some interval. Okay, so the analogous concept would be, we want a PDF, which is going to be a joint PDF, and we want it to be constant on that square and 0 outside the square, right? So that just captures the notion of being, completely random point. As we're picking a random point, x comma y, We want a completely random point in the square, so we want the density to be constant all over that square. So 0 outside. Let's find the joint PDF. Well, the joint PDF, therefore, from what I just said, is some constant c when if x and y are both between 0 and 1, and 0 otherwise. Now, in one dimension, if you integrate the number 1 over some interval, you get the length of the interval. In 2 dimensions, if you integrate the constant 1 over some region, you get the area of the region. So if we integrate this thing, we get the area. So the integral is area. So c equals 1 over area would normalize it, which equals 1, because the area of that square is 1. So the joint PDF would just be 1 inside here and 0 outside. And if you want the marginal distributions, then just integrate out the, integrate this dx or integrate this dy, you'll get 1. So marginally, x and y are independent uniform, which is pretty intuitive. Uniform 0, 1. Which is kind of intuitive, right? Because it just says if you pick a random point in the square and the x-coordinate, it's uniform, the y-coordinate is uniform. So that's pretty straightforward. That's an example of independence. But I want to contrast that with an example of dependence, where instead of a square, let's use a circle. So suppose we want uniform in the circle. I'll say disk for clarity. A circle might just mean the circle. We want everything inside. So on the disk, x squared plus y squared less than or equal to 1. Okay? So let's see what that looks like. So we just draw a circle. Sorry, it doesn't look like a very good circle, but pretend that that's a perfect circle centered at 0 of radius 1, and we want to be uniform in here. Okay? We want to write down what's the joint PDF, what are the marginal PDFs. Okay? So first of all, for the joint PDF, but by the same kind of reasoning, it's just because it's uniform, that means another way to say uniform is that the probability of some region must be proportional to its area, right? It's analogous. In one dimension, I said probability is proportional to length for a uniform distribution. Here, probability is proportional to area. So because of that, the normalizing constant has to be 1 over the area of the circle, pi r squared, so that's pi. So the joint PDF is 1 over pi inside the circle and 0 outside. And a common mistake with this kind of thing is to then think that, oh, that says that they're independent because this is just a constant, so it doesn't, it looks like I can factor 1 over pi as like constant times a constant. It's just a constant. But they're not independent because of this constraint. They're actually very dependent because, for example, if x is 0, then y could be anywhere from -1 to 1. But if x is close to 1, then y has to be in some tiny little interval, right? So if we fix x to be here, then y could be between here and here, right? So the values depend on where that is, knowing x constrains the possible values of y. That says that they're not independent. So here x and y are dependent, and we can, in fact, we can show that given that x equals x, then we can actually say, well, what can y be, right? Y has to be between square root 1 minus x squared and minus that, right? Because x squared plus y squared less than or equal to 1. So this depends on x. So this is the constraint, okay? So we might guess that y is uniform between here and here. That is, if x is here, then y, we know it's between here and here, but could be anywhere, right? So a good guess would be uniform, but next time we'll do an integral to show that for practice. But you can see right now that they're dependent. Okay. So see you on Friday.